Hi, everyone. Welcome to the RMK lecture, a distinguished lecture. I'm Shafi Goldwasser, and this is a lecture series that we are extremely proud of. It's in honor of Dick Karp's achievements, contributions to computer science and theoretical computer science. And it was established due to a very generous gift by many people in honor of Dick. It's celebrating everything he's done for computer science. And we are especially fortunate today to have Daniele Micciancio from UC San Diego. And Daniele is the leader of the research on the lattices and their applications of cryptography going back many years. In fact, I'm very proud to say that Daniele was a student of mine and in my team many, many years ago. And he has done fundamental work on showing the hardness of certain lattice problems, on designing cryptosystems, designing homomorphic encryption systems with a lot of innovations that are used throughout any system that actually does homomorphic encryption today. And today he's also a gifted speaker, lucky for us, and he's going to speak on lattices, post-quantum security, and fully homomorphic encryption. And Daniele is a visitor in the lattice program this semester. In fact, he was about to fly from San Diego. He was on his way to the airport when they declared that there was going to be a shelter at home. So he stayed in San Diego. Welcome, Daniele. Thank you very much for giving the first remote RMK lecture, fully remote RMK lecture. Daniele.
Okay. Thank you for the introduction. Thank you for the invitation. I'm happy to be there, virtually at least. And so I'll be talking about lattices, post-quantum security, and fully homomorphic encryption. So encryption is the main topic. And encryption is the classic problem, is the tool used by cryptography to solve the classic problem of secure communication over an insecure channel. So you have two people, Alice and Bob, that want to exchange a message in secrecy. And there's an eavesdropper that is intercepting their communication. So Alice and Bob can still achieve secrecy if they share a secret key or a pair of public and secret keys that are used by Alice to encrypt the message under the public key, computing a ciphertext which is sent to Bob, and Bob can use the matching secret key to decrypt the ciphertext and recover the original message, in this case just hi. And if an eavesdropper that does not have access to the secret decryption key will not be able to get any information on the message. Now, modern cryptography rests on a solid mathematical foundation, and the approach used in cryptography to build a secure solution to communication problems and other problems is to start from hard mathematical problems. And the classic problem used by many cryptographic functions these days is the factoring problem. The problem of factoring a large number, say the product of two primes, P and Q. So given the product P times Q, you want to find P and Q. And this is a problem that is considered to be hard, at least in the classical setting. Now, using the mathematical problem and this hardness, you want to exploit this hardness to build a cryptographic scheme that achieves some security goal, for example, encryption. And the approach of modern cryptography is to exploit this hardness to build cryptographic functions that achieve their intended security goal in a provable way. So showing that if you were able to break the encryption scheme, then you would be able to solve the corresponding hard mathematical problem, in this case factoring numbers. And if you just take the logically equivalent contrapositive of this implication, if you assume that factoring is hard, then you can rest assured that the encryption scheme is secure. There is no way to break it unless some big breakthrough in mathematics occurs. Now, all of this, specifically for factoring, changed some 25 years ago when Peter Shor came up with an efficient quantum algorithm that can factor numbers. Now, this algorithm couldn't be run at a time. It still cannot be run today because we don't have quantum computers, or at least quantum computers that are big enough to run that algorithm. But the fact that it is theoretically possible to use quantum physics to build computers that are able to solve the factoring problem pretty much puts this factoring problem out of business for cryptography. It means that the assumption that factoring is hard does not hold in a post-quantum world, a world where large-scale quantum computers have been built. And the same holds for many other cryptographic schemes that have been used in the past and are still used to these days, including schemes based on the discrete logarithm problem in finite fields or over elliptic curves. And so this calls for new mathematical problems that are hard even assuming that quantum computers have been built and can be used to run Shor algorithm or other algorithms to attack them. So lattice problems are a class of problems that seem to fit the bill, at least as far as we know. And but before talking about lattice problems and lattices, let me first introduce the problem using subset sum. Now, subset sum is a classic simple problem that involves only the addition operation. So you are given a set of integer numbers, A1, A2, up to AN, and also a target value B. And the question that you have to answer is there a subset of these numbers, A1 to AN, which, if added up, give you precisely B as a result? Now, this is the classic subset sum problem, and these numbers are often called weights of the subset sum. Then they are just integer numbers. And this problem is, there are several variants of these problems, and some of them are called the knapsack problem. That's an alternative name for the same or very similar problem. And in this setting, the problem is defined in analogy with the problem of packing a knapsack. You have a knapsack of a certain capacity B, the size of the knapsack, or the maximum weight that you can carry with it. And then you also have a collection of items of different size or weight. And the question is if you can fill the knapsack up to capacity using a selection of those items, so you can make optimal use of the capacity.
Daniele,
yes?
There's a question in the chat asking, didn't IBM manage to factor 15, the number 15, using Shor's algorithm?
Yes, I can also do that. It is 3 times 5. And yeah, so I think that so it's very interesting that you can build a proof of concept showing that in principle the algorithm is workable. We just don't have computers that are big enough to run it on numbers that are large enough to be interesting by cryptography. Now, if you're using 15 as your RSA modulus, well, you don't need the quantum computers to be hacked, and I can do that more cheaply. I'll charge less than IBM if you want to factor numbers of that size. Okay, so I don't have the chat open, and so if anything comes up, so I count on
yeah.
you're happy to let me know.
Do you have the Q&A open? I can move things from chat to Q&A.
Oh, I don't have anything open. I can try to open it, but I need to find a. So let's say Q&A.
I could just read it to you. That's fine.
No, I have an issue with the window. If I open the window, then it resizes the slides, and then it might cause problems with that. Okay. Anyway, I'll go over all the questions at the end. And reply at the end. Okay, so let's move on. So this is the knapsack problem, and so there are different variants. Sometimes you consider variants where the items can be used multiple times, not just a subset, but a multi-set of them. And well, this problem seems deceivingly simple. It only involves addition, a much simpler operation than multiplication. But well, if you think it is easy, then I invite you to try it out next time you go to your favorite restaurant, and you can see if you can get your desired order. And of course, once this pandemic is over and we can all go back eating out. Okay, so the problem is hard. In fact, it is NP complete, and it is not just an NP complete problem. It is one of the problems from the original list of 21 NP complete problems studied by Karp back in 1972. So this is a landmark paper that established the field of NP completeness by showing that a large number of problems of interest in computer science are all equivalent under polynomial time reductions. So we can say that the knapsack problem or the subset sum problem has been known to be NP complete pretty much since people have known about NP completeness at all. So it's a classic problem, and being NP complete, it seems a very good candidate as a problem that cannot be solved efficiently in polynomial time, either using classic or quantum computers. So under standard assumptions like P is different from NP or NP is not contained in BQP, we do not expect any algorithm to solve this problem efficiently. So lattice cryptography, it is something that is closely related to using the knapsack for cryptography. I'll show you in a moment what a lattice is and what the relation is between lattices and subset sum. So it's not surprising that people have been trying to use the subset sum problem or the knapsack problem to build the cryptography. And in fact, the first attempts to do so started already in the 70s, in the late 70s, when Merkel and Hellman proposed a knapsack-based public key cryptosystem. However, the system got broken by Shamir and Lagarias and Odlyzko, and incidentally, they used the lattices to carry out the attack. And still, it seemed like a good idea. And many variants of the knapsack problem used for cryptography kept being suggested for almost 2 decades, but they were always broken one after the other. And perhaps all these attempts and designs, proposals, and failures of the knapsack-based cryptography are best epitomized by the title of the paper of Odlyzko called "The Rise and Fall of the Knapsack Cryptosystems," which pretty much shows how people felt about it in the early 90s. Now, all of this changed in the mid-90s when ITI reached a turning point, showing that there is a very interesting connection between the worst case and average case complexity of lattice problems, closely related to the knapsack and subset sum problem. And in some sense, we can think of this result as showing the right way, the correct way to use knapsack and lattice problems to build cryptographic functions. So as people were about to completely give up at using lattices and subset sum for cryptography, we found a good way to do that. Now, so what is a lattice?
I want to read something from the chat, which is, I guess, relevant to these last 2 slides from Vaselin, saying D-Wave can do any 3-digit number. This is for factoring, but does not use Shor algorithm, but reverse multiplication circuit, and it's building series application for the knapsack problem. This is D-Wave. I mean, just.
Oh, okay. So that's very interesting.
So maybe that's something that could, at the end, could be discussed, unless. Yeah.
So we will have to finish at 12 sharp, in fact, 5 minutes to 12, because there's another talk on the same line, I think. So, but yeah, so I'll be happy to discuss this offline or in some other follow-up meeting. So I'll be there virtually at the Simons Institute for the next several weeks. So yeah, you know where to find me. Okay, so Moving on, so what is a lattice and how does it relate to subset sum? Now, the typical lattice problem is just a variant of the subset sum problem, where instead of adding up integer numbers, you add up vectors. So it is something that is very, very similar. You can still describe it as a subset sum problem, but it is a subset sum over a different type of object, an n-dimensional vector. Now, you can also, so these vectors are added up using the standard vector addition operation, component-wise. And you can consider standard subset sum problems over vectors, or you can also consider variants where you take not a subset, but an integer combination of the input vectors with small coefficients. You can even use negative coefficients as you like, but the key feature is that the coefficients should be small. So in some sense, lattice problems and subset sum problems are the same type of problems. It's just that lattices with their n-dimensional structure are often more convenient to use in the design of cryptographic applications. So just to show you what a lattice looks like, you have a collection of basis vectors. In 2 dimensions, you can only draw 2-dimensional lattices. So you're given 2 vectors, B1 and B2. And you take the set of all the integer combinations of these 2 vectors, B1 and B2, which produce the set of intersection point of an n-dimensional grid. Now, so this provides a nice geometric intuition of what a lattice is. This is often very useful when designing cryptographic algorithms, when designing algorithms to solve lattice problems. However, in the design of cryptographic functions, this is not that critical. It is possible to just use a standard matrix formulation without pictures. And I will not be using this geometric visualization of lattices in the rest of the talk. So lattices in the construction of cryptographic functions will be something more closely related to the matrix formulation of linear algebra. You can take the weights of your knapsack problem, A1, A2, and so on. So these are vectors. You can put them one next to the other, forming a matrix A. Now, selecting a subset of these vectors or a small linear combination of these vectors is exactly a problem of matrix vector multiplication. You have a matrix A and you multiply it by a vector X. So it's a linear function. And the knapsack problem, given the output of this function, B, asks to, and given also A, which describes the function, asks to find an input X which produces the correct output. And one important feature of this function is that it is linear. So it's the simplest type of, not the simplest function would be the constant one, but it's one of the simplest type of functions you can think of. And the fact that you can build the cryptography out of it is quite surprising. And but more than that, so this linearity property, which at first was considered a potential weakness and a reason to be concerned about the use of knapsack in cryptography, this also can be the key to some of the attacks to subset sum based hash functions. So this also turns out to be useful. And as we will see, lattices with their linearity property can be used to do some amazing things, not just to design cryptographic functions which are secure against potential quantum attacks, but also to build very powerful cryptographic primitives. Now, notice if you just describe this as a linear function, so this is not a hard problem. Computing the function is a matrix vector multiplication, and you can also easily invert the function. You can easily find a solution X to the system AX equals B. you can do it using Gaussian elimination or your favorite method to solve linear systems. So the problem becomes hard when you restrict the input to be a short vector. For example, a 0, 1 vector if you want a subset sum of the columns of the matrix A. Now, if you restrict the input to such a subset, which is a nonlinear, nonlinear subset of the input space, then you have the problem of finding a small solution to a system of linear equations which cannot be solved using Gaussian elimination or any other non-efficient technique. So this provides a one-way function, a function which is still easy to compute. Given A and X, you can easily compute B, which is the product A times X. And but it is hard to invert, where inversion requires to find a small input X, which is 0, 1, or more generally bounded by some parameter beta that describes how small should a vector X to be considered a valid solution to this problem. Now, in many cryptographic applications, there is a slightly different formulation, which is often used, and that's called the learning with errors problem. The two problems syntactically can be related one to the other using lattice duality, but I will not talk about that. But since this is the formulation we will use in the rest of the talk, let me briefly describe it. So in the learning with error problem, you are given a matrix A. This time it is a matrix which has typically full column rank. So it has longer columns. So the height of the column M is bigger than the number of columns N. So if I were to give you A times S, then even if S is small, you could easily find it using Gaussian elimination just because the solution is typically unique. So A times X is an injective function. So in order to make the problem hard to solve, we add an error component E to the product A times X. And the learning with error problem asks, given A and B computed this way, can you find a secret S, a short vector, or even a long one, a long vector S, such that AS plus E is equal to B? So S here can be arbitrary, but E, the error, should be small. Now, even if you add this error, this function is still injective, and that's what makes the learning with error problem much more useful to build applications than the subset sum problem I described before. And you can think of this as an injective version of ITI's short integer solution problem function. And so this problem was, in this formulation, was proposed and proved by Regev in 2005, showing that under similar assumptions as those made by ITI, this problem is still hard, and assuming that lattice problems are hard even for quantum computers. Interestingly, Regev original reduction used the power of quantum computing to transform one problem into another. So it was a quantum reduction that produces quantum algorithms, even if I were to give you a classic algorithm to solve LWE, the learning with error problem. Now, and not only the problem is hard to solve in its search version, it is hard to invert this function and recover S. Regev also showed that the output of this function, this vector B, is pseudo-random. It is computationally indistinguishable from a uniform vector in the range of the function. So an n-dimensional vector with entries modulo Q. So this Q is just a small integer modulus, which is used so that this lattice problem can be formulated as a problem over a finite group. And Q is not a hard to factor number, doesn't have to have any specific structure. And the source of hardness in this problem is the fact that these matrices have a non-trivial size. So you have a matrix with n columns and m rows, and as you increase the number of columns, for example, performing an exhaustive search over all possible secret vectors S becomes not feasible. Now, this hardness result of Regev was later improved by Packard in 2009 and by Brakersky et al. In 2013, showing an almost equivalent classical version of Regev reduction. So we are confident that this problem is hard, and we also have a good way to use it in cryptography. But how it is used in cryptography. So what I'll describe now is how to build a very simple object, which is a private key encryption scheme. So we use the fact that the output B of the learning with error problem is pseudo-random. So it will look random to any adversary that does not have the secret key S. So we think of S as being the secret encryption or decryption key. So here I'm talking about the private key encryption, not public key one. So both the sender and receiver use the same key S. And since B is a value which will look random to anybody else, you can use it to build an encryption scheme using it essentially as a one-time pad. You can use it to mask your message M by adding B to it. And so this will look random to the adversary and hide any partial information about your message. So the message consists of an LWE output, which is AB, to which you have added M. Or if you want, you can think of it as having the LWE pair AB, to which you added the matrix 0M, which can be interpreted as an insecure encryption of M. It's a ciphertext of M that does not really hide M.
So, Daniele, I'm confused. You're using M in two places here.
Yeah, sorry.
You mean the green message, yeah?
I mean the green one, yeah, but I don't know how to change the color of the pen, but yeah, you can ignore this, this index, yes. So these are different things. So this is the message, and here I'm adding, yes, the message.
And you're talking about vector addition here?
Yes, it is vector addition, and but here M is actually just a single, so B in this setting is just an integer, so there is no M here. It is actually an integer in this specific example. You can extend this scheme easily using bigger matrices, so you can encrypt a vector at a time. But so in this case, M, even the message M is just an integer, but it is a different integer than the number of rows, of course. Sorry for the confusion. Okay, so similar encryption schemes were proposed using a problem called the learning parity with noise, which is essentially the same as LWE, but using a modulus equal to 2. You're performing addition of bits, and the length of vectors is measured in the Hamming distance. And so this had already been proposed back in the early 90s. And so this paper actually proposed a pseudo-random generator and a stream cipher, if you know what it is, using the problem, and a description of a block cipher, pseudo-random function or encryption scheme using this type of problem was explicitly described by Gilbert et al. In 2008. So Regev LWE essentially is a generalization of this problem with larger modulus, where Q instead of being 2 is a polynomial in the dimension n of the matrix. Okay, so let's look at the decryption algorithm. You can decrypt your ciphertexts in a pretty easy way. What you do is given A and B also has this message M component added to it, you take the second component and you subtract from it A times S. Now, using the definition of B, you can just carry out this operation and see that as a result, you get exactly M plus the small error that was added to the LWE instance to make it hard to break. So you see that from this algorithm, what you get is not the message M, but a perturbed version of the message. So in some sense, it is a noisy decryption algorithm which does not recover the message exactly. It gives a corrupted version of the message. But this problem is easily solved by using some form of error correction. So for example, you could reduce the message space to consist of only the multiples of, say, Q over 4, where Q is the modulus. So this is a discrete set where different messages are at distance Q over 4, one from the other. Now, if the error which is added to a message is less than Q over 8, then all these orange regions consisting of a perturbed message will be disjoint, and you can recover the exact value of the message exactly by rounding it to the closest multiple of Q over 4. So we will not be concerned about this error in the rest of the talk, though it plays an important role in the design and analysis of applications. You have to be very careful about it in the applications so that the error can be corrected. But there is a standard way to do it. Now, so this is the basic encryption scheme, how to use LWE for encryption, but I want to do more than that. So the reason lattices became so popular these days is not just because they offer a potential solution to encryption in a post-quantum world, but there are also many interesting, powerful applications that build on lattices. Now, specifically, you can build an encryption scheme which supports the computation on encrypted data. Now, standard encryption schemes allow to encrypt your data, store it in a secure way, then retrieve it or transmit it, but that's all you can do. Now, in a fully homomorphic encryption scheme, you can encrypt your message, ship it to an untrusted server, and the untrusted server can compute on it. So if you give a program F to this server, the server can run the program on the encrypted data without decrypting it, without even knowing the decryption key. And it will come up with an encrypted version of the result of the program. Now, this opens up the door to many interesting applications of encryption, where encryption is used in a more dynamic way. Now, fully homomorphic encryption is a classic problem in cryptography. The concept was originally proposed back in the late 70s by Rivest, Adelman, and Dertuzos, but back then it was just an open problem. Nobody knew how to solve the problem. It was not until recently that a first candidate solution to the problem was found. In 2009, Craig Gentry found a first candidate solution, and more importantly, he introduced a bootstrapping technique that proved to be critical in all the subsequent constructions. Now, there's been much work after that, providing efficiency improvements, better security guarantees, implementations, and libraries that I will not be able to talk about. What I want to do in the rest of the talk is to give an idea of how all of this works and how you go from just addition, which is a very simple operation, to not just a secure encryption scheme, but an encryption scheme that supports arbitrary computations. So I will do this in a mostly informal way, omitting many technical details, but trying to convey the main ideas behind many of the known constructions. Now, it shouldn't be much of a surprise that lattice-based encryption supports homomorphic addition. That is, given two ciphertexts, you can add them up, and the sum of two ciphertexts, if you just do your algebra, you will see it is the encryption of the sum of the two messages. So you have here two expressions representing the encryption of M1 and M2. And if you add them up just as matrices, so this is a simple matrix addition operation. So if you do that, you can factor out the secret S and express it as the sum of A1 and A2 multiplied by S. Similarly, you can group together the two error terms and you can group together the two messages. So if you use this notation, encryption of M with noise at most beta as a way to represent all the ciphertexts encrypting a certain message with a bounded amount of noise, then you can see that the sum of the encryption of M1 with the encryption of M2 is an encryption of M plus 2 with a noise, which is the sum of the noises of the two original ciphertexts. And similarly, you can also multiply your ciphertext by a constant C. And as you perform this product, and this is just a scalar matrix product, it's a very simple operation. If you look at the definition, you'll see that the message is being multiplied by C, and also the error is being multiplied by C. So this means that you can also multiply a ciphertext by a constant, but you can only do so if the constant C is small. If C is large, then the error gets multiplied by a large number, it will become too big, and then you will not be able to decrypt. So, up to this point, we have a method to take linear combinations of ciphertexts with small coefficients. So the linear combination has small coefficients. Now, we would like to do more than that. And a first simple thing that can be done is to multiply ciphertexts by arbitrary, possibly large constants. And this can be done by defining an enhanced encryption scheme. Here I'm calling it encryption prime. And so in this enhanced encryption scheme, you encrypt not just the message M, but you also encrypt, using the original scheme, multiples of M. And you don't need to consider many of them. You just take multiples that are equal to M times the power of 2. And so with logarithmically many ciphertexts, you get a ciphertext of the new scheme. And now you can multiply them by any constant C, simply by writing C in binary. And once the constant C has been written in binary, you can express the multiplication by C as a subset sum of those messages. So you can take a subset sum where you select the ciphertexts that have a binary digit in the constant C equal to 1. Since this scheme supports the computation of linear functions homomorphically, you can take this summation inside the encryption, and you can factor out the M, and you can recover the constant C inside the ciphertext. So now we have a scheme that allows to compute arbitrary linear functions. You can multiply your ciphertext by any constant. And now notice the result is, so you're starting from this enhanced encryption scheme, E prime, and the result is a different encryption scheme. But it is easy to extend the scheme to produce results according to the original encryption scheme, E prime, simply by multiplying your ciphertext not just by C, but you can also multiply it by 2C, 4C, 8C, and so on. So if you do this, then you will get the result according to the same encryption scheme as you started with. So, so there is a standard way to convert, to use this linearity property also to achieve public key encryption. But just in the interest of time, since we need to finish early, let me skip that. And let's move to a different operation, which is multiplication. Now, addition is not much of a surprise that is supported by lattice-based encryption because it is a linear problem. But is it possible to multiply ciphertext? Is there a way, given an encryption of M1 and an encryption of M2, to obtain the encryption of the product M1 times M2 with a noise that is possibly a function of the noise of the original ciphertexts? Now, this operation seems to go beyond what you would reasonably expect from lattices and subset sum, but surprisingly, this can be done. Now, the reason this is surprising is because if you can do multiplication, then you can perform arbitrary computations. So if you represent your bits as zeros and ones, then all the operations, all the binary operations like negation, logical AND, logical OR can all be expressed as a combination of linear functions. For example, 1 minus x correspond to logical negation. Multiplication gives exactly addition, it gives exactly the logical AND of 2 bits. And you can also express the logical OR of 2 bits if you also have at your disposal a multiplication operation. So being able to do both addition and multiplication is the key to do anything you want, to perform arbitrary computations. So, so how can you multiply ciphertexts? Now, it is quite surprising that the linearity property of subset sum and lattices allows to do that. And in fact, it allows to do that in several different ways. There are different ways to exploit linearity to achieve multiplication. And you can do it by nesting encryption functions using tensor products of ciphertexts. You can use it, you can do that using the linear property of the decryption, or you can even do it by combining some of the bootstrapping technique which is needed to perform arbitrary computations together with a computation of a simple binary gates. Now, different methods that are used to multiply ciphertexts, that's the main difference between different lattice-based encryption schemes. So all lattice-based encryption schemes by and large use the same encryption function, the same decryption, the same method to add ciphertexts. Sometimes they use different encodings of the messages, but to a large extent, they are essentially the same encryption scheme. So the main difference between different schemes is how multiplication is performed. And I want to quickly review these 4 methods to perform multiplication, just in a couple of minutes per method, to give an idea of the variety of techniques that can be used to build homomorphic encryption. Now, let's start with encryption by nesting. Now, so you are given 2 ciphertexts, C0 and C1, which encrypt messages M0 and M1 under a scheme that is linearly homomorphic. So how can you multiply these 2 ciphertexts? Well, you can multiply C0 homomorphically by C1. So at this point, you might object that, oh, well, that's what you want to do. That's the goal. What do you mean? You don't know how to do that. Well, you want to multiply C0 homomorphically using C1 as a linear transformation. Think of C1 as being a constant. Since C0 is a linearly homomorphic ciphertext, you can multiply it by a constant value C1. Now, if you do so, you can bring this C1 inside the encryption scheme that protects M0 and get an encryption of M0 times the constant C1. But M times C1, the value that is encrypted under S0, again, by the linearity of the encryption scheme used to build C1, is an encryption under a possibly different key of M1, which is multiplied by M0. So you can take this M0 and bring it inside this encryption computation. So if you combine these 2 steps together, you see that the final result is the encryption of the product M0 times M1, which is encrypted under 2 schemes, first under S1 and then under S0. So it is a nested encryption, which can be decrypted if you know the 2 keys. You just first peel off the first layer of encryption, and then you peel off the second layer. Now, interestingly, since both functions are linear, also their composition is linear. So the resulting scheme still supports addition. So after you've done this multiplication, you can perform additions of ciphertexts. So, and the approach extends also to multiplying longer sequences of messages and ciphertexts. You can multiply 3, 4, 5, as many as you want. Now, there are many details that are technically very critical, which I omitted. So, for example, the fact that you can only multiply on the left, not on the right. And these ciphertexts, as you nest encryptions, get bigger and bigger. And but this is the basic idea behind this multiplication method, which was proposed by Gillard et al. Back in 2010, crypto, but actually based on a paper that, so a preliminary version of the work already existed in 2008, even before Craig Gentry bootstrapping breakthrough. Now, this is an interesting, simple approach to perform multiplication, but it is very limited in terms of what you can do. As these ciphertexts get bigger and bigger, you can only perform a very small number of multiplications. In fact, even using an improved version of the scheme, which is from 2011, I think you can only perform at most a sublinear number of multiplication. And in the paper, it is made clear that the scheme does not support bootstrapping. So you can perform addition and multiplication. You can use it to evaluate low-degree polynomial, but that's where it stops. Now, let's look at a different method to do multiplication. So this one is called multiplication by tensoring. Now, let me start with a trivial method to perform multiplication. Now, you can do multiplication symbolically. If I give you two ciphertexts, M0 and M1, and I tell you, oh, multiply them together, you can just concatenate them and then append a symbol that says, oh, I want the product of them. Now, how do you decrypt it? You decrypt these two component ciphertexts individually, and then you perform the multiplication on the result of decryption. Now, of course, this is not interesting, and it applies to every operation. It's very powerful, but it's not really giving you anything useful. And the reason is that the size of the ciphertext grows with the computation. In fact, it will be linear in the computation size. So most definitions of homomorphic encryption rule out this type of solution as trivial, by requiring that the decryption should be sublinear at least in the size of the computation that was performed on the ciphertext. Now, why is this useful? So how can we go from this to something useful? Well, this trivial multiplication method is way more than what you need. Now, if I give you both C0 and C1, if I give you two ciphertexts, then you can compute any function of them, given this trivial multiplication. But in practice, that's not what you need. This seems unnecessary. You just want to decrypt the final ciphertext. You don't want to compute arbitrary functions of the ciphertext. So what you want is a combination of C1 and C0 and C1 that supports the computation of the decryption function. So what does this decryption function look like? So if you go back to the definition, you'll see that the decryption function is linear. Now, so if you decrypt two ciphertexts and then multiply the result of decryption together, then you will get a function which is bilinear in the ciphertext, C0 and C1. So this suggests that instead of using the concatenation of C0 and C1, you can take their tensor product, which by definition supports the computation of any bilinear function. Now, this computation is more efficient than the trivial one. In particular, after you've computed these tensor products, you can still add them up together and support homomorphic addition. And there are several optimizations that are possible using the fact that you don't even need to compute arbitrary bilinear functions. You just want to compute bilinear functions corresponding to decryption. So this is the second multiplication method, and since we don't have much time left, I will skip so this is basically based on the work of Brakowski and Vaikunthanathan, which also introduced a method to change the key under which ciphertexts are encrypted, and that can be used to keep the size of the ciphertexts bounded, which is useful to perform arbitrary computations and support a larger number of operations. So let me move to the next. So I'll skip the key switching and let me move to the third method, which is multiplication by homomorphic decryption. So in this setting, so you use the fact that the decryption is linear, not only in the ciphertext, but it is also linear in the secret key. So if instead of using the secret key, I give you a multiple of the secret key, then when you decrypt using this scaled secret, you will get a scaled version of the message. So by using different secret keys, you can multiply the message. Now, so the fact that you can use these alternative scaled secret keys provide a method to perform multiplication of ciphertexts. The idea is to consider these secret keys that have been multiplied by C as an encryption of C. So we can perform a decrypt and multiply operation where when you perform so normally when if instead of giving the secret key, I give you an encryption of the secret key, when you perform decryption on an encrypted secret key, you will go back the encryption of your starting message. But if instead of using the secret key encrypted, you use the encryption of a multiple of the secret key, when you compute this homomorphic decryption, you will get an encryption of a scaled message where the message has been multiplied by C. So you can think of this as an encryption of C and use that as a method to perform multiplication. So,
Daniele,
yep.
just wanted to remind you that you have 5 minutes left.
Yeah. So I'm. So let me move. So I hope this gives a little bit of a flavor of. So this is something that I talked about in some.
Can I just ask a question? Who is it that just spoke? Is it Jesse?
Yeah. Yes.
No. Can we just move the other talk 5 minutes? It's not.
The talk is from another department.
Okay, let's not waste time. I'll go on and we can, so we'll, So I'm almost there. So this scheme is somehow, that I just described is somehow related to the encryption scheme of Gentry, Sahai, and Waters. Now that scheme, as described in their work, had a different intuition. The intuition was that, ciphertexts have approximate eigenvectors and eigenvalues. So when you multiply a ciphertext by S, you will get the secret key, you will get a multiple of S where this approximate eigenvalue is the message that is encrypted by C. And so this provides a method to do a multiplication, because if you multiply two ciphertexts together, when you multiply it by S, you will get first S times M2, and then the result will be multiplied by M1. So you see that S is an eigenvector, approximate eigenvector of the product, C1 times C2, but with an eigenvalue which is the product of the two original eigenvalues. Now this seems very different from what I described before. In fact, the intuition is very different. Conceptually, these are two different schemes, but if you look down at the operations which are performed at the very bottom level, they are the same operations. So in some sense, so these are technically equivalent encryption schemes. So let me briefly describe, there's only one slide, one last method to perform a multiplication, which I called gate bootstrapping. The idea is that, so this bootstrapping operation, which is needed to perform arbitrary computations on ciphertexts, can also be used to get for free the computation of a very simple operation. So you can do multiplication. So we are not done yet because this error is getting bigger and bigger. So bootstrapping, I will not describe it, I will skip it, but is a method that is used to remove this error. And let me skip the description of bootstrapping, but let's see how it provides one more method to multiply ciphertexts. Now, think of M1 and M2 as being bits. They are 0 and 1, but instead of thinking of them as values modulo 2, we think of them as value modulo a larger modulus, 3 or 4. Now, if instead of multiplying M1 and M2, you add them up, you will get either 0, 1, 1, or 2. So you get something which still has enough information to tell what their product is, their product should be 1 only when the sum is equal to 2. In particular, it can be computed by taking the sum, dividing the sum by 2, and rounding the result either to 0 or to 1. So you can perform multiplication by adding the two ciphertexts and then dividing the result by 2. An operation that can be performed essentially for free during bootstrapping. Not for free, at the same cost as, with no additional cost over bootstrapping. And that provides one more method to multiply ciphertexts. Okay, so there are many more FHE schemes that have been proposed in the literature, but I think that they can be classified pretty much based on how multiplication is performed and fit into one of those 4 categories. So let me conclude with a brief summary. I described the lattice-based cryptography, a method to encrypt messages which provides both conjectured resistance against quantum attacks and also a very simple method to adapt ciphertexts together homomorphically. And somehow surprisingly, this also allows to compute the product of two ciphertexts, and this leads to FHE, fully homomorphic encryption, which supports the computation of arbitrary functions on encrypted data. And so this is still a very active research area with many open problems, both in terms of improving efficiency of homomorphic encryption and also security, specifically when you encrypt a key under itself, which is needed for bootstrapping. Okay, so thank you for your attention. This concludes my talk, and this is just a list of the papers that I didn't mention explicitly during the presentation.
So Daniele, I want to say, first of all, thank you very much for a great talk. I very deeply apologize for this press time. And what I'd like to propose is that there's probably a lot of questions and people would like to have some expansion on the stuff that you skipped, like the multiplication methods, especially 3 and 4. I know that's true for me. So since we don't have time for questions, because apparently we're gonna have this link hijacked from us due to some, I think, misunderstanding, maybe I can send a link out to, we can find a way to send a link out so that we can have another 15 minutes to ask you questions and so forth, okay?
Yeah, that's fine. Yes,
So
that's good. So I'll stay available and wait for a link so we can move the meeting to a different Zoom.
Yeah, so at this point, before they hijack for us, if somebody wants to ask a question, let's open it for people, either panelists or any questions from the audience. So I guess my question is the following. It's one way to compare the 4 methods that you described for multiplication. And can you do a quick comparison of which one should be used when, or which one clearly is better in terms of efficiency?
Yeah, so of these 4 methods, the last one, in some sense, it is the easier to use because it allows to compose the operations any way you want, because you're doing bootstrapping all the time. But currently is still not the fastest one. I think it may become an attractive solution in practice, but it's not quite there yet. It's the newest. Now, the previous method, the multiplication by tensoring, is the one the previous one, which is the GSW method. So GSW is used for implementing the bootstrapping decryption, the bootstrapping procedure of the 4th method. So in some sense, it is already being used there. So these last 2 methods have the advantage of being based on hardness of lattice problems within polynomial factors. So if you are concerned about using the weakest possible assumptions, those 2 are the best choice. The first and second method, in some sense, the second method is a more efficient version of the first. So the first doesn't seem interesting at this point, other possibly for just presentation purposes. And so the second method is the one that is currently most efficient when you have to perform many computations, which are also parallelizable, assuming you can make an assumption that lattice problems are hard for super polynomial factors, and that's basically the BGV BFV method implemented using ring lattices for efficiency. But that's so that's the second method. So, but I think all four methods are still interesting even now as techniques for which we may find an interesting way to use it. For example, the third method is used inside the bootstrapping procedure of the fourth one. And since all these methods are using the same basic encryption function, there is even a possibility of combining them together. So rather than just moving to the latest from the research perspective, I think it's interesting to still think of all these possibilities.
Okay, wonderful. So we do have a link, and it's just been sent to all the attendees. So whoever wants can switch to that link to stay, and whoever wants to ask Daniele more questions. Okay.
Okay.
I think
so,
you have it in your. I think you have it on the side in the chat, Daniele, because you are a very important component. If you don't.
yes. So I'll move there. So yeah.
Thank you.